All right, thank you, everyone. This is our second session of the Applied Data Science Invited Speakers track. I'm honored to introduce Nina Mishra. She's a principal scientist at Amazon, where her research interests include health AI, search algorithms, and privacy. Most of her career has been in industry including Microsoft Research. Her work has product implications including machine learning, related algorithms, and many services in Amazon's cloud and in Microsoft search engine. Her academic experience includes being an associate professor at the University of Virginia and acting faculty at Stanford University. She is driven by the transformative potential of health AI to revolutionize the lives of millions worldwide. And her talk today is going to be charting pathways to AI-enabled healthcare. Without further ado, Nina.
Can you hear me? Okay. Can you also hear me this way? Perfect. Today, nice to meet everybody here. Good afternoon. Today I'm going to be talking about how we can create pathways to provide physicians the best health AI tools possible and patients the best healthcare possible. But I want to begin with a story about me because my background is in the theory of machine learning, and I came across health AI in a somewhat serendipitous way. I was working for a company that had a mobile search engine, and we were tasked with providing a better search experience for the query Justin Bieber and 1040 tax return. And I could not get excited about this problem. So I decided one day that I was going to search through the search logs and see what people were asking. So I looked for any question that contained how do I, why do I, where do I, what do I, and to see what people asked. And I stumbled upon this query in the mobile logs, which was how do I do CPR on a 13-month-old toddler. And CPR stands for cardiopulmonary resuscitation. It's the process that you perform chest compressions on somebody, and it appeared to be a woman who was frantic with her child who had 6 minutes to live, and she was trying to learn how fast and how deep to compress in that moment. So it was a very powerful moment for me because I knew people were coming to the search engine for Justin Bieber, but I had no idea that they would rely on a search engine at their most life-critical moments. And I knew exactly how the search engine worked, and it wouldn't have done anything to help her. So what we did was we created a partnership with the Stanford Emergency Medicine Department. We realized that the sensors on the phone had the answers to her questions. And we created a new CPR where you put the phone on the person's chest directly, and then you perform compressions on the phone, and we integrate the accelerometer one time to get the speed of compressions and another time to get the depth of compressions. But anyway, this story happened a while ago and it lingers with me because I felt that we had such an opportunity to help people at such an important junction. At Amazon, I work in the cloud, AWS, Amazon Web Services. And I have the great fortune of talking with hospitals and physicians and surgeons and primary care doctors. And they ask me a lot of questions, which are hard, they're important, and you have to get it right. I'll give you some examples here. One example is, I do surgery. After surgery, I'm noticing that people are dying more often from this condition. And I don't know why. Can you tell me why? So we get questions like this. We get questions about personalized medicine. I've got 2 types of medications I can give a patient. Medication, red pill, works well on some people. Blue pill works better on other people. How do I know which one to give to whom? Another example, I have a patient who's on a ventilator. I'm going to take them off the ventilator. Are they going to need it for the next 48 hours? If not, I'm going to send them home to our home hospital program. And a 4th type of question that we get asked is, can you reliably do early warning of conditions like sepsis? So with 12-hour notice, can you tell us that this patient is going to escalate and feel and experience one-way organ damage? So you can see these are very serious questions, and if they happen to one of your family members, you would really want any AI tool that gets used to get the answer right. So these are great questions. I'm going to talk about the problem that we have that's underlying all of these questions, which is the fact that We don't have a data set that includes everybody. What happens today is the hospital will come and they will say, hey, can you build us a model to do blah, blah, blah. We train a model on the data from that hospital, and then we test it on data from that hospital A, and we say, oh, that looks really good. That's going to work. And the internal AUC is good. Then we take that same model and we move it to a new hospital, hospital B, and when we test on that hospital, it doesn't work, and we lose the trust of physicians in the process. So the answer, oftentimes when it doesn't work, what we do in ML is we say, oh, that's out of distribution. But you can't do that with the patient. You can't say you're out of distribution. What we notice is that the external AUC, this has been reported in the literature, will drop by 7 to 25%, basically making the ML model useless in a new hospital system. And there's a variety of reasons for this. If you train a model on data in the US and you test it on people in India, there's a big demographic shift, right? Distribution of prior conditions change, the environment changes, maybe air pollution is different. And so you can't just take a model and just deploy it in another location. And there's also equipment differences, maybe higher resolution or lower resolution equipment. So what I believe is the biggest problem we face right now is that if you take a condition and you take people around the world, they all experience this condition in different ways. And their data is spewed across many different hospital systems, right? This data is fractured across different hospital systems. And if we are to reliably solve some of these very hard questions, we need to find a way to bring all of this data together if we are to truly revolutionize healthcare. So it's not about one hospital, we want to do it with every hospital's data set. So the key takeaways for this talk are going to be, number one, what I've already mentioned, that our health data is fractured. Number two is that if we want to help the next billion people, we need to get data from the last billion people. And in order to do that, we have to find ways to protect privacy. And that's going to be the topic of today. How can we do this in a privacy-preserving way? And the technical tool that we're going to use is to find a way to sketch the data, add noise to the data, and then publish that. And we want to do it in a repository setting where everybody can get access to the data. And so that's the final thing, is how can we make these public repositories where all hospitals can put the data that they have into some kind of public location so that everyone can use it, scientists and other hospitals as well. So the grand challenge I'm going to talk about today is, can all hospitals share medical records while protecting privacy? This is a grand challenge. Nobody knows how to do it. You're not going to get to the final answer of this either by the end of this talk. We're chipping away at the problem, and I'm going to talk about that particular aspect of the problem that we focused on, which I'll mention in just a second. But whenever I tell people, like, oh, you can't share medical records because they're private, they're like, well, no, this is easy. Just take the names and hide the names. That'll preserve privacy. And there are tools like that. So there's one called Filter, PHILTER, which removes personal health information, such as name, social security number. And here, what you see on the left is a fake medical record. And on the right, what you see is the result of applying Filter on it. You see it does a great job. It hides the name, Jane Doe, it hides the social security number, so that looks good. So you look at the thing on the right and you go, yeah, that looks anonymized, I don't have any more work to do. But there's still quite a bit left, which is that it's a 30-year-old female who has cirrhosis, a history of alcohol abuse, and hepatitis C, and was admitted because the veins in her esophagus are about to burst. That's quite a bit of information. And in fact, you can take this to the extreme level and hide the entire clinical record and only keep the diagnosis codes. Like, so what people were diagnosed with, these are the billing codes that are used in the United States, the ICD codes is what they're called. And so to show this, a hospital went and they took a data set where they found ICD codes and then DNA sequences. So their thinking was like, oh, we're just gonna put ICD codes, you're not gonna be able to figure out who they are. But by joining it with their hospital records, they were able to uniquely re-identify 96% of the population. So hiding the whole record and just keeping the codes is enough to figure out who they are. Another thing to think about is there are external data sets that people can bring in and start to join with the data that does get published. So the state of Washington, for example, publishes records, but they hide the name and they only keep the social security number. And what this scientist did is she paid the state of Washington $50 for the medical records, and then she went into newspaper articles and searched for accident, right? And so here's an example of someone who was in an accident, and it has their name, Richard Bolton. I made this up. This isn't real, but it had the hospital that they went to, it has the time, and it has the date. And then by joining these two together, she was able to re-identify 43% of the records. So you can't just hide names. Like it feels tempting, like I just hide this PII, it's gonna work. It's not enough. So going to the other end of the extreme, where we're not just hiding things, you might be asking yourself, we asked ourselves this, which is like, can I use an LLM to make a medical record? So here's a question, generate a synthetic medical record to an LLM. And what it does is it creates a very structured data set, very nicely organized with patient information, vital signs, chief complaint, history of present illness. It does a good job. And so we thought, well, maybe we can use an LLM to make medical records. Maybe that'll solve our problem. But the challenge is like, let's say I want to get data from a stroke center. If I just start asking an LLM for data, I may not get the kind of patients that would come to a stroke center. Like this one is about someone with a heart problem. So we take a little tiny departure and tell you about a paper called Tiny Stories, done by Eldon and Lee, where what they did is they said, oh, we want a corpus of children's stories. How are we going to do that? We'll just ask an LLM. It'll make us 1 million children's stories. But the variance in the stories is very limited. They're all like pretty similar. But with prompting the LLM, they were able to get a richer variety of children's stories. So we're going to do the same thing here. And as this talk progresses, I'll show you how we can prompt an LLM with terms, keywords, to get the kind of records we want while preserving privacy. So in this example here, we prompted it with blurred speech and facial droop, and you can see in the record that it definitely generates a patient with slurred speech and facial droop. It even makes up something, left arm weakness, which is a very good symptom that typically accompanies people that have a stroke. So this is what we're getting to, and like to give an outline of what we're going to discuss today, the first thing I'm going to do is talk about how we can estimate density privately. This algorithm then, I'll show how it can be used to generate private medical records. And then I'll take a step back and talk about how this technical tool that we developed, which is generating a sketch of your data and adding noise to that sketch, can be used in other contexts. And I'll get to that towards the end. So let me start with private density estimation. So the definition that we're going to use during this talk is something that's been around for a couple decades by now, called differential privacy. And what it says is that if you are looking at two data sets, D1 and D2, and they differ in only one person, your algorithm is differentially private if, and that algorithm here is called M, capital M, if an attacker who sees what you publish on D1 and D2 is essentially undistinguishable. So if a person is in the data set or they're not in the data set, the output looks essentially unchanged. Specifically, it differs by an epsilon amount. This epsilon is the differential privacy parameter. The smaller this value is, the more privacy you have. The way to achieve this definition is through something called the sensitivity of a function. The sensitivity is how much does a single person's data change the outcome. So if one guy can change the outcome wildly, you have to add more noise to protect that guy's data. So that's the sensitivity. And the function we're going to be talking about is density estimation. And we want to know how much can density estimation change by adding or subtracting a person. The sensitivity is a really important concept because it directly ties to how much noise you have to add. The more sensitive the function is, the more you have to protect that guy who could change it, the more noise you have to add to the answer. So instead of giving the exact answer, what you're going to do is give an answer with some noise added. The noise that you add, the standard deviation of that noise, is proportional to the sensitivity of the function you're trying to estimate. And this picture here shows you what the Laplace distribution looks like. So we're going to be using this. And then the nice thing about this definition is that if an attacker has some external knowledge, say they've read every news article, or say they've seen everything on the internet, the guarantee here is no matter what they knew before, what they're going to learn from this is very little about a specific person. And that very little is quantified by epsilon. So let me talk about the problem we're going to be focused on, which is density estimation. What do I mean by density estimation? Well, imagine that we have a hospital, and then there's a scientist, and the scientist is trying to figure out, like, how common is stroke? And we want to give an answer, 0.23%. Okay, that's the question we're trying to answer, but we don't just want to do it for one query, we want to do it for lots of queries. So we want to figure out something that the hospital can publish so that anybody, other scientists, other hospitals, can go and figure out what is the incidence of blood thinners, what is the incidence of embolism, et cetera, in the data. So this is the problem we want to solve. It's called the function release model. Function because the hospital is going to basically produce a function that will enable anyone to compute this f of x. F is the density. So this is the question we're going to try to solve, which is how do I privately estimate the density of phrases in a hospital's medical records? So now you might be saying, well, gosh, is that really private? Like what? I mean, can't you just give the exact number of people that have that condition? The answer is no, you can't, because there are rare conditions such as primary cardiac lymphoma. Only 200 people in the world have it. So if I ask a hospital the question, what is the incidence of primary cardiac lymphoma? If the answer is, 0, then the person I know near the hospital who has that condition doesn't go to that hospital. If the answer is bigger than 0, then I know that that guy goes to that hospital, and I've broken differential privacy. So that's not going to work. You can't give the exact answer, but you can add noise to answers. And so here's how you go about doing it. Here's a simple algorithm, which is a histogram. So you take all the phrases that appear in your data set, you make a histogram, you count how many patients have it, and you can't publish this, as we just said, because it's private, but you can add noise to it. So if a given person can say every person contributes 3 keywords, then the noise you would add is like 3 over epsilon. And the result is that you get these blurry counts. Instead of the actual count, you get some kind of noise added to the count. And now what you notice is that if you add the same noise to every bucket. So if a count's really high, you're going to add essentially very little noise. And if a count's very low, the number's essentially going to be like uninterpretable. And so that's how you preserve privacy. This works. This will give you a way to estimate density privately. But it has 2 limitations. The first is that there are terms like clot and blood clot in this example, which appear as different buckets, but they're really the same thing. And so they should be counted as the same thing. The second problem is that there are terms such as facial droop, which are missing in this data set, but they're obviously connected to stroke, but they're somehow not here. And so they never get counted. So the way we're going to get around this is by moving to a world of embeddings. So this is the result of applying some of these very common keywords, applying them on the embedding model BioBERT. So we're generating a 768-dimensional vector for every term in the data set, and then using t-SNE to plot it in 2 dimensions. So this is what the embeddings look like. In case you've never looked at this before, there is some really nice structure in how the queries end up getting embedded together. In the upper left, what you see here are clot-related terms. A clot in your brain, in your lungs, in your feet, they're all here. And then on the bottom left are kidney-related terms, like chronic renal failure. On the bottom right, what you see are heart-related terms, arrhythmias, rapid heart rates, slow heart rates, atrial fibrillation, etc. So these embeddings are great. The geometry is really going to help us. And this is how we can get 2 terms which are very similar. We'll end up getting embedded nearby. But this doesn't give us density. This just gives us a location in R to the D. So the way that we're going to convert this into a density is using something called the kernel density estimate, which I will define now. Intuitively, all it is you're going to take points in your data set. Every time you get a point, you drop a Gaussian on it. And if you have a term that's very common, you're going to drop a lot of Gaussians on it, and there's going to be a lot of density there. To estimate the density at a point y, then what you do is you sum up the contributions that you get from all the other Gaussians. You take e to the minus xi minus y squared, and sum that up, and then take the average. That's the kernel density estimate. And if you apply this to the data that's coming from this, like, fictitious stroke center that I'm talking about, then what you will get is a kernel density estimate that looks like this. So this picture here, you'll see there's more density around terms like clot and blood clot and stroke, which is what you're getting out of the stroke center. But the other nice thing is that the term facial droop, which didn't appear here, once you embed it, ends up appearing here. And you can figure out the density, you can triangulate it based on the Gaussians that you've dropped on the other points. So this is what we're going to do. We're going to look at density estimation, but we're going to see how we can do this privately. So private density estimation. The query comes, I want to figure out the density of facial droop, and what we want to return is the kernel density estimate plus some noise. And I'm going to talk about what kind of noise you have to add in order to protect privacy. And this is done with my collaborators, Tal Wagner and Jonathan Namad. So without privacy, if you want to figure out what is the density at facial droop, you can take the distance from, say, facial droop to clot, square it, take e to the minus that, and then take the distance from facial droop to stroke, square that distance, and keep doing e to the minus that. And this in a linear time algorithm, linear in the number of points, and linear in the dimension, this is a key thing, you can figure out the exact kernel density estimate. But with privacy, the prior work that was out there, the best algorithms ran in time exponential in D. And what I'm going to show you now is how we broke this exponential barrier to estimate density privately. And the intuition comes from something called random Fourier features, which, if you haven't seen before, looks like this, so that there's an equation on the bottom right here. And what you see here is that if you want to estimate this kernel density, e to the xi minus q squared, you can express it as the product of these weird cosines. And I'm going to explain to you intuitively why this is not a bad idea, but I'm not going to prove exactly how they got to this because that would require more time. But essentially what you do is you take this W, you pick a random direction W, you project your data onto this dimension W, and once you do that, and you add a random offset B, you will get the points, the blue, green, yellow, and black points on this line. And then if you look on the right there, what you'll see is wrapping this circle, wrapping the points around the unit circle, so that the x value is cosine wx plus b, and the y is sine wx plus b. And what happens is that if you have two things which are really close, like let's say you take facial droop. Facial droop is very close to clot in reality. Once you take this random direction, you project onto this random direction, they'll also end up being close. And then when you take the cosine, they'll have similar signs. And so they'll both be either +1 or they'll both be -1. And you end up, when you take the expectation over many of these, you'll end up getting something that's a big number. But if you take something like kidney failure, which is far away, then once you project it onto this line, kidney failure is going to end up getting embedded very far away from the others. And so sometimes, once you take the cosine, sometimes they'll be +1, -1. Sometimes they'll have the same sign, sometimes they'll have different signs. And that number isn't going to be as high as when two things are close. So this is the intuition, and it can go wrong sometimes if you have something like fever here, this red point fever, which ends up getting embedded close to clot, but that's because it's an unfortunate choice of W and D. And so to get around this, which is like very similar to other hashing techniques, you choose many different W's and B's, you check the expectation of that, and then you can estimate the kernel density. What's brilliant about this is it allows us to separate what the hospital would do from what a scientist would do. And specifically, the hospital can focus on the cosine Wx plus B for their patients, and the scientists can focus on cosine WQ plus B, where Q is facial droop. So here's the algorithm that we use to estimate the density privately. The hospital will publish a random direction W, a random offset B, and they'll also publish the sum of cosine Wx plus B. This isn't private yet. This is just to show you how you would do it with this random Fourier sketch. So you get this, and now if you repeat this many times, then you will get multiple W's and multiple B's. And that's what the hospital will publish. Random directions, random offsets, and then the sum of cosine Wx plus B for each of these WI, VIs, right? The scientist now will take its WQ plus B and multiply it by each of the capital FIs, and then take the median number. This is how you would do it without privacy. With privacy, you just have to look at the sensitivity of this function. And the sensitivity of this function is small because cosine varies between -1 and +1. And we're going to take m of these, so that's why you have m in the numerator. But since you divide by x, you're also going to divide by x. So this ends up adding a little bit of noise to each of these. But with more and more choices of random w's and random b's, you do have to add more noise to all of the answers. So that's something to consider here. And what we can prove is that this algorithm is epsilon differentially private, number one. Number two, we can prove that it approximates the actual kernel density for every query you might ask with high probability. And that probability is probability at least 1 minus eta, which means that an eta fraction of the questions may not be answered correctly, but the remaining 1 minus eta will be answered with a good additive approximation. And this is assuming that you take enough of these random Fourier sketches. There have to be a lot of these different directions, W and different B's, in order to assure this. So what's nice about this, as I mentioned earlier, is that the hospital can focus on their data and publish what they want. A scientist can then come, whatever query they have, they can start multiplying it with these random Fourier sketches and then estimate the density on their own. That's the nice thing about this. And then the hospital, in turn, can share these W, B's, and FIs, and anyone can use it. And this is accurate for an infinite number of queries, as I mentioned, so many scientists can ask many queries. But the best thing about this is that it runs in time linear in N and linear in D. Before, the best algorithms ran in exponential in D, so this algorithm basically breaks that exponential barrier. To show how an algorithm would work, not exactly this algorithm, but a sister algorithm in our paper, how it works on a data set, I want to show you on the left here is a data set which is patients who have diabetes, and this is how long they stayed in their hospital as a function of their age. Without privacy, you get this kernel density picture on the left, where there's a lot of people who are 65 years old who spend 2 days in the hospital. On the right, with epsilon 0.1, using a method in our paper, we showed how the kernel density estimate gets blurred a little bit. This is just in 2 dimensions, so you can see how the picture looks. In 100 dimensions, here's how the error changes as a function of the number of random Fourier features. So each line here is a different choice of epsilon. The black line is no privacy, and the other lines are different values of epsilon for more and more privacy. And there's a little bit of a knee here in the curve, which is important because you can't just keep, like for exact accuracy, you want to do as many W's and B's as you possibly can. But remember that the more W's and B's you choose, the more noise you have to add. And so there's a point of diminishing return here where more random Fourier features don't help, but you still can get pretty good accuracy. And this like bend in the curve is where we would focus the algorithm's attention. So that's how you can estimate the kernel density estimate with privacy. So that's the first part. So now we want to go to the second part, which is how do we use an algorithm that can estimate the kernel density effectively? How do we use that to generate medical records? And this is done with my collaborators, Supriya Nagesh, Justin Chen, and Tal Wagner. So our ambition here is to make private synthetic text. Okay, so what we're going to do is we're going to take a real record. This is what the hospital would do. It would take a real record and it would extract the phrases. There's tons of medical taggers out there at this point. And the phrases it might extract here are shortness of breath, peripheral edema, and fatigue. So once it's extracted these keywords, it constructs the kernel density estimate of these keywords, a private kernel density estimate. Now, what we would like is an algorithm that could sample from this private KDE. We don't know how to do that. While you can do that with exact KDE, with our private KDE, we don't know how to do that. But what you can do with medical data, for example, is come up with a medical dictionary. And now you can estimate the density of every term in your medical dictionary. And we know how to do this. It doesn't matter how many queries you ask. And then you start sampling from this dictionary. You can sample sample independently. So every time you draw a word, you just independently pick another word. We also have in our paper a way to sample this in a dependent way. But I'm just think about this independently for a moment. In practice, we can't just use an unlimited dictionary. In practice, we found that if we give up some of the privacy budget to winnow down the size of this dictionary, it improves the performance of the algorithm. Now we have samples of keywords, and now we just prompt an LLM and say, hey, LLM, make me a medical record with these keywords. And that's the algorithm with privacy. We maintain privacy because the keywords were drawn privately, and then we just use an LLM to make a record. So how does this work? So I'm going to give you two ways of evaluating this algorithm. One is by just publishing the keywords, because the hospital at this point, it can stop and it can publish the WBs and Fs, or it can publish the keywords, or it can publish the medical records. But if we just look at the keywords, suppose you publish that. So here's how you would use it for a downstream machine learning task. And suppose you want to distinguish between patients who have heart failure and patients who don't have heart failure, just as an example. Then you would make a KDE, one each. One's for the people who have heart failure, one for the people that don't. And you start sampling keywords. And you give that to a scientist. They do their embedding magic. They train an ML algorithm. And then they send that classifier back to the hospital. This is one way to use the algorithm. Another way to use the algorithm is to actually go to the last stage and make the medical documents. One using the KDE for heart failure, another using the KDE for people that don't have heart failure. In this case, if a scientist goes and trains a classifier on that text, we do have to use domain adaptation because the language that's used at a hospital may differ from the language that's used by an LLM. But here's a result on a MIMIC data set. MIMIC is a publicly available data set of medical records, and we're doing it on this two-class classification, heart failure or not, using the BioBERT embedding model. In addition, we tried it on DBpedia because there's nothing about these results that are restricted to healthcare. It's what drove us to work on the problem, but it works on any data set. So here it's a 14-class classification of DBpedia data. These are Wikipedia summaries, and the classes are, company, artist, athlete. So we're building one KDE per class, and then using the sentence-BERT model to embed the data. And here's the result. Here's the classification accuracy that we're able to get. So the bottom row of this table, and this is just with keywords. This is not with LLM-generated medical records. It's just with the keywords. The bottom line here shows you the result of training a model on the original data, no privacy. So we get 80% at distinguishing heart failure from not. And then what you see is with varying values of epsilon, what the result of prediction is. And it's about 75% no matter what, 74% no matter what value of epsilon you choose. For DBpedia, the accuracy is about 85%. But as you vary epsilon, as you weaken the privacy requirement, you get a more and more accurate classifier. If we go to the last step and we generate the medical records, then something interesting happens. The results get worse for MIMIC and they get better for DBpedia. So it's 76% without privacy for MIMIC and 80% without privacy for MIMIC on the phrases. So the text gets worse. But for DBpedia, the text gets better, and you can do 97% accuracy. And then you can see here, like for MIMIC, doesn't really matter what the epsilon is, it's getting about 71%. And for DBpedia, the accuracy improves as you relax the privacy requirement. And remember, we need domain adaptation to get this to work. There's a lot of future opportunities for work to do here. And one of them is that we're right now just extracting keywords. We were just focused on how do we estimate density privately so we could get keywords. But in reality, a medical record has a ton of structure, and we should be extracting a knowledge graph and then doing it. So a record might say right lung shows sign of embolism, left lung shows no embolism. So then if we extract keywords, we get embolism, no embolism, right lung, left lung, right? But we need to know what modifies what in order to really understand the record. So that's, I think, an important direction. And then another is that these records are multimodal. I've only focused on the text here, but they have time series of heart rate, SpO2, blood pressure, et cetera. And they have imaging data. They have chest x-rays. They have pathology information. And so we need ways to make multimodal records as well. So that is how we make medical records. And now I want to get to the third part, which is how do we now take a step back and look at the solution that we came up with, which is like we make a sketch of the data and we add noise. How good of a solution is that? It turns out that this is a very nice way of thinking about how to preserve privacy. You end up adding less noise, you end up getting pretty accurate answers, and I want to talk about how we use the same technique on a different problem. And it's like there's a community of people that work on this, it's not just us, but I'm going to show you another application which is a little bit different, and that is how can you join data privately. So the context is the following, and this is a COVID problem. We have a hospital, and then we have an airline. And the question that they want to answer is, do people who take long-haul flights, are they more likely to get a respiratory infection? I mean, so I guess a lot of us took long-haul flights, but question like, does that make us more likely to get it? And the challenge is like, the hospital knows who got what respiratory infection. The airline knows who traveled where, but they don't know about each other's data. The airline has no idea who got what respiratory infection. The hospital has no idea who flew where. But together, what they want to do is jointly estimate some function of their data. And there's many applications of this. Many companies that want to get together, they're like fantasizing about having columns in their data, which they don't actually have, and trying to figure out if they can do learning from their data to other institutions' data. So here's another one where you might want to figure out, do people who work near a toxic waste site, are they more likely to get cancer? So this work I'm going to describe was done jointly with my collaborators, James Cook and Millen Cheyenne. So we want to do private joins without an interactive protocol. So the hospital here has labels which are, does this person have a respiratory infection or not? And on the right, the airline has information about who took what long-haul flight, are they a frequent flyer, what kind of plane filtration system did the plane have, etc. And I'm going to describe our solution in a very simplified setting so you can see how it looks. And this simplified setting assumes that the sender here, who's the hospital, has more people than the receiver does, which is the airline. Each person appears once, and et cetera. I can go through this later, but the hospital has the names and who had a respiratory infection. So what's tantalizing about this question is that the very data you want to join on, which is like, say, their email address, is private. So you want to join on PII, and yet you want to derive a conclusion about the join of the two data sets. So is this like even possible to do? So it is, and here's a simplified setting where you can get this to work. So you have the hospital's information. What they do is they use a hash function, H, which maps their name to a random value between 1 and B. This B should be big enough. And then it puts whether or not they had a respiratory infection in that bucket. Now, in order to preserve privacy, you flip labels in the data set. So for people who were in the hospital's data, you flip it with some probability. And you keep it the same with the remaining probability. And for everybody else, you just put random noise. And what we can prove is that if you flip a coin with probability, say, half e to the minus epsilon, think of epsilon as 1, so it's like 1 over 2e, then you can preserve differential privacy. But furthermore, if you give this data set to an airline, so you give them this hash, this noisy hash H, and you give them the sketch S, they can go and look up people in their data set and create this column of respiratory infection in their data and then go and train an ML algorithm. And we can prove that that ML algorithm will be accurate even though we've added noise. So we've added noise, we've protected privacy, but you can still draw large-scale conclusions about the data. And here's an example where we have synthetically done this, where we have the label is held by one party and the features are held by another. The labels end up getting published in a blurry way, and what you see here, like, is what you expect as you increase epsilon, that your accuracy improves. Without privacy, you get like 98%, and with less and less privacy, you get improved prediction. So that's the third thing. So let me just give you the key takeaways from my talk. Coming back to this, we did describe this in the beginning. Number one, medical records are fractured into data from multiple different hospitals. If we are to unleash the next generation of new healthcare breakthroughs, we have to find ways to bring all this data together. And we have to do it while protecting privacy. We've given one method here, which I think would be really valuable to use. This technical tool of sketching your data and adding noise to the sketch is really valuable for protecting privacy. And it's going to take a community effort to build these public repositories that anybody can use. And I think this is what's the tipping point that we hit with LLMs, is we got so much data, anything that anybody had ever been written, married with the best hardware, and we could do next token prediction in such an amazing way. We have to get to this point with healthcare data. We have to be able to find a way to merge all of these data sets together with privacy so that we can also hit that tipping point. We can build the health AI tools that will enable physicians to operate more effectively on their patients, and we end up giving the best healthcare to patients as well. So that's what we're looking for. And we're also hoping not only hospitals, but maybe other organizations put their data into this, imagined data lake. If you'd like to play with the private KDE code, there's the GitHub link here. And if you'd like to collaborate on creating such a public repository, here's my email address. Reach out to me. Thank you.
Thank you very much, Ina. We do have time for a couple questions. People can line up on either side of the aisles. I do have a question. While you were presenting results on Mimic versus the other data set, it was a little interesting that the Mimic one was like, no matter how epsilon changed, you didn't see it. Like, is it an artifact of the data? Like, what was happening?
Oh, can you hear me? Yes. Okay. I feel really uncomfortable being glued to this podium, but yes. We also thought it was a mystery why we weren't seeing the DBP. With DBpedia, we were seeing like the natural progression we expected. We did not see it with Mimic. I don't have a good hypothesis for why, but the gap was actually smaller with Mimic than it was with DBpedia. So once you get to the real data, the gap was huge with DBP. It was like 97% if you had the real text, but like 85% even at epsilon, like high values of epsilon. Yeah, so I don't know. And maybe the LLM hasn't seen these medical records before, and that's influencing it. I'm not sure, but yeah, it's a good question.
Sorry, this might be a slightly ignorant question, but I was just curious that, do you think that this, or if you've already experimented with different languages, and I'm just wondering if medical records in other countries would be shaped differently or defined differently, or does like that make a difference here?
That's a beautiful question. It's hard to get access to medical records for me, and imagining getting that in a foreign language is like, it feels so out of reach. I feel like I've hardly looked at enough records in the US, much less globally, but I think that is important. If we are going to make synthetic medical records and it only works in English, we failed like a great fraction of the world. So that's another reason why I think we need these giant common repositories from every hospital. So this is not designed to be like American hospitals. I want it to be every hospital in the world. So thank you for calling out that important point. Yeah. And lingo between hospitals, they change. They call different things with different names, like, pneumothorax gets called PTX sometimes. So there's, and I don't know if that happens in other countries. So they might have their own lingo. Yeah.
Hi, thank you for your talk. I read differential privacy papers initially when they first came out of interest, so I'm not an expert on differential privacy. What I remembered from that was the utility for, once you apply differential privacy, the threshold, the epsilon, which is the added noise, dictates the utility of the final data set that you get, right? So, and then that utility could potentially change based on what end downstream tasks that you're trying to do with that data set. So what you're proposing right now, if you were to just apply differential privacy, and then I understand there's transformations involved to do density estimations, but in the end, you're literally creating a data set that is based on certain epsilon value, a certain amount of noise that's injected. How do you guarantee that that published data set, without publishing data set for different noise levels, that data set is going to be good enough for other people who are like now researching other questions that you don't know what those questions are?
Yeah, great question. So your point is that it might be that I need a different value of epsilon depending on the downstream tasks that I'm after.
Yeah. Unless you publish all epsilon values, which is then negating differential.
But then, so it's a great point. And in these examples, we're actually like playing with the values of epsilon and trying to gauge what is the impact on downstream classification. And we can see that like the more privacy you want, the worse the downstream classification accuracy. So we know for sure that this is true. But then to be able to enable it for any downstream task, you're right, that you need to play with the epsilons to see which one's going to work for which downstream task. Because this is an open question. We don't have, I can't say epsilon is 1, and then let's go home.
So can I take your previously published data sets with different epsilon values to de-anonymize people?
Yeah.
It's the same idea that you presented earlier, right?
So say again?
So if I can I take differently noise data sets that you've published before and overlap them or link them together to de-anonymize people, right? Because it's the same problem.
Yeah, so every time you publish a data set, so this is important in your case. So if I publish a data set with epsilon 1 differential privacy, and then I publish the same data set with epsilon 2 differential privacy, now I've lost epsilon 1 plus epsilon 2. So I'm giving up epsilons every time I publish a new data set. This is also important on a stream. Like if I publish now and then I want to publish 10 years later, I give up extra epsilon each time. Yes. Yeah. That's the way differential privacy is. Yeah. I don't have a solution to your open problem yet.
We have time for one last question.
Okay. Thanks for those so awesome sharing. Because you just talked about if you want to extract the data from the medical record, we need to scan maybe the dictionary. Yeah. So I have another thought is because we have documents about ICD-10. It's classified by the maybe the government or NIH. Or maybe we can use the ICD-10 because the document provides several disease and some keyword. Maybe we can use this keyword or disease to synthesize the data, do the augmentation, and use this data to scan the test in the medical record.
Okay, so are you asking whether you can take the text of the ICD code and use that to be the basis of the embedding?
Yeah, I think maybe it's a solution, another solution.
Another solution, for sure. You can focus on the text of the ICD codes. That would give you some kind of information about the embeddings. And you would just focus on the ICD codes, which, that's another way to do it, yeah. We were trying to make more of the text around it, but the ICD codes are a great first step. Yeah, thank you for the comment.
Thank you very much, Nina, for that great talk and answering all those questions.